All right, so let's get started. So once again, thank you everyone for joining us today. My name is Matt and I'll be leading the presentation today. We're going to be talking about the timber design workflow effectively. And this webinar today is going to be a little bit different than some of the other ones that we've done. We're really trying to scale down the length of the webinar and really focus more on the technical content and the presentations, less slow on slide data and so on. This is the first webinar that we've done like this, and we do have a few more scheduled like this. It's an experiment for us. We hope you like it. We'd love to hear your feedback as well. But really, our goal is to focus in on a specific point, keep the length relatively short, and we can always elaborate on other topics down the road as well. So as I mentioned, my name is Matt. I'll be presenting today. I'm going to start with a really brief intro to S-Timber. Then we're going to talk about mass timber section design, as well as have some time for Q&A at the end. So S-Timber, if you aren't familiar with S-Timber, is available through the Structural Engineer or Advanced Structural Engineer suite. So if you're already using S-Frame or S-Concrete and you have this suite of tools available from Altair, you actually already have access to S-Timber, whether you know it or not. And it's a very powerful interface that you're working with. We like to think of it as intuitive with its ability to customize the workflows and layouts of everything that you see. It also has some automation capabilities that we'll touch on in just a minute. It does offer a more parametric modeling environment when you compare it to something like S-Frame, which is maybe great for modeling finite elements, but less so when those elements might need regular updates and so on. So this gives you that flexibility. It's also using S-Frame solver behind the scenes. And what that means is that this isn't some nascent solver that has been untested in industry. It's been around for over 40 years and trusted on projects around the world. Now, we are talking about design today, and I think it's important to touch on the types of design that S-Timber is capable of. It can do design of CLT panels, it can do glulam design, sawn lumber, as well as steel section design. And in today's demo, I'm really going to be focusing in on glulam and looking at sizing my glulam elements and the workflow associated with that. S-Timber supports the Canadian, American timber and steel design codes at the moment, as well as building codes for wind load and seismic load generation and load combination generation and so on. And one of the features that if you've been following S-Timber for a while, perhaps you've taken advantage of this or you're at least aware of, is that S-Timber, amongst some of our other tools as well, offers access to S-Frame's open API through an integrated Python scripting interface. So within the software itself, you have a platform to access the API, customize and automate different tasks to your likings. Now, as far as member design goes, we're going to be focusing in on section size optimization for timber, glulam specifically, but this can also be used for steel members as well. And there are other different types of design available in terms of connections and panels and so on. It starts with a definition of design groups, which I'll talk more about later on. These basically allow us to group members together that are all going to be given the same cross-section through the design process. And we also need to assign section lists to those design groups. So section lists are basically a subset of your section database that can be considered during the design process. You may want to exclude certain sections, or you may want to order it a certain way, and you have control over that. And when you run the design, S-Timber is going to suggest for you the optimal solution or the optimal section for your design groups. And it's possible to override that design as well. You can also set up different criteria to consider for the design. Do you want to sort based off of which one gives you, the lowest depth, or which one might be ordered first in your section list? There's different criteria that you can apply. So rather than dwelling on that in the slides, let's jump right into this the presentation. I apologize if I feel a little bit different today. I'm not used to this type of presentation format, so I am learning as we go as well. So this is a model I'm going to be working on. It might appear a little bit odd to the initial inspections that we have, but you can see here we've got a bunch of CLT panels that are sitting on top of a glulam timber frame. And if I look at the framing view, we can see that we have beams going in a variety of directions, and this is something we'll consider with the layout of our design group. Now, what also might look a little bit odd is it looks like this thing is effectively supported by toothpicks. This was by design, no pun intended. We wanted to basically set this up in such a way that we know that it's going to be failing code checks initially. So this is perhaps representing an extreme situation where we have no idea what section size is going to be used in our applications, and we want STimber to optimize the sections for us. So I've actually run an analysis already ahead of time. I'm going to go to the result menu here, and you can see here that I'm looking at some of my different utilizations. So on the right hand or left hand side, I have this code check utilization field in the tool window that's showing me the load case or combination that I've selected and the code check that's being displayed. So right now it's showing me the Timber member axial code check, and you can see I have a variety of utilizations ranging from infinity, which is actually basically just telling us that these members are slender and it can't perform the axial check on those, to even less than 1. Less than 1 meaning that our demands are less than capacity, a few that are 0, so some that don't have any axial loads in them. And I can view this graphically, or on the right-hand side here, in the design output window, I can also see this information numerically as well. So I can click on the top of the field that I'm interested in, and I can see the member axial, bending plus axial, two-way bending, bending code checks all failing due to different loading scenarios that we have. So if I look at one of them, like let's say I want to look at two-way bending or member bending here, I can see that, and I can see which load combination might be causing that issue. In this case here, it is the 0.9 self-weight plus 0.9 dead plus 1.4 wind. And mostly just my columns along the, I'll call this longitudinal direction, the long side that are failing this code check. So you can imagine here, if we wanted to optimize this, we'd want to make sure that we group our design sections together in a way that's going to be practical. Because we know that some of the sections are failing worse, or some of the members are failing worse than others, there may be different cross sections that would be valuable to use for our columns, for example, than for our beams. So we can set that up in our designs to do that. So the first step would be to basically go through this approach and look at different ways that we can set up these designs. Right now, maybe I'll just dive into the existing geometry a little bit more, first of all. And I can see here that, again, we know we are using small cross sections. My column, for example, if I left click on it with the selection tool, is showing me that I have a glulam 80 by 114 cross section assigned. I actually have the same thing for all my beams. I just made it simple for myself. Glulam 80 by 114, but you'll notice we have this design group field that is set to none. So we haven't defined any design groups yet. I also want to point out here, just I'm jumping around a little bit, but there was a point that I wanted to address, was the quantities that are calculated by STimber. It might be a good kind of way for us to observe the difference in mass and materials that are being used. So I can click on this quantities field, and I can see here the total length of glulam 80 by 114 cross sections that I'm using, 240 meters, and the total mass. Again, this is deliberately undersized, and we're well under designed for this particular scenario. So this number shouldn't really seem realistic to anyone. But we're going to focus in on this. We can actually drill down into these details, and I can see the member results. And it will actually show me for each member, or each cross section rather, the cut length that's required, and the actual mass of each one of those lengths as well. But let's go ahead and start thinking about our design groups. We may want to group some of the members together in different ways. For example, I'm going to assume that I have all my columns as part of the same design group. So if one of those columns is designed or is utilized higher than the other columns, the cross-section that works for the highest utilized column is going to be applied to all the different columns. Now, we can obviously fine-tune this, but that's what I'm going to say for this particular scenario. So I'll go to the Define menu, and I'm going to go to Design Groups. And I'm going to set up a design group. I don't have any yet, but I click on the Add button. And here I'm going to give it a name. I'll just call this Columns. I'm going to choose the member type, if I can find my mouse, which is column again. The material that's going to be used, which is going to be a glulam material. And then a section list, which I've actually set up ahead of time. And this is basically just a subset of the database that I'm interested in, or perhaps a composite of several different databases that I want to consider for my design. So I've selected I've got two here. I've got a columns database, which basically looks at all the different cross sections that might be adequate for my columns. And I have a beams database, which we'll look at later. And I can also choose a section that's going to be considered for my initial best guess of the design. I'm going to match that to my original analysis section. So here I can click apply, and I've got that one design group defined. Let me add another one here. This one's going to be called longitudinal beams. And for my longitudinal beams, I'm going to basically use the same information with the exception here that the section list is going to come from my beam section list, which might have a different set of sections from that section database. And it's also going to start with the original section that I had. Click apply, and I'm going to copy this one as well and just have a second one, which will be transverse beams, and everything else will remain the same. So I've got 3 different design groups that I'm going to apply to my model. And with that, we can start selecting the elements that we want to apply these to. So I'm going to select my columns. And under the members field here, I can assign that columns design group ID, as we can see here. I can do the same thing. If I maybe switch to my top-down view, I might want to apply some additional design group data. So I'm going to say I want my longitudinal sections here. Let me make sure I've selected everything. Sorry, my mouse is a little bit jumpy today. It's a new hardware that I'm using on a live presentation, which is always a bit nerve-wracking. So here, as we go around, and if my mouse, maybe I'll zoom in a little bit more. Wasn't jumping around on me so much, this would be a little bit easier. But you can see what I'm doing. I'm basically selecting my subset of elements, and I could have done this ahead of time, but I was lazy, and I'm selecting it now. And you can see here that basically we're going to have all the elements that are longitudinal to our model, and they're going to be part of this design group. So let me just switch my view here and make sure I've got everything else. I want to add these guys as well. I think this was an easier view for me to work with. And I'm going to send this to the longitudinal beams, if I could spell that correctly. And finally, I have my transverse beams, which is going to be basically everything that I haven't done so far. Now we do have kind of like an elastic band selection, but this is easier just to make sure that I haven't over-selected my elements in any way. And these are all going to go to the transverse beams design group. So with this, maybe what I'll do is I'll just walk through the process of running a code check first of all. So here I can go run analysis and code check, and this is going to basically allow us to repeat what I had done ahead of time already. So I can go through and I can run a structural analysis for all my load cases and combinations. And I can also run a code check, which is going to compare those structural analysis results, which will be the demands on my structure, to the design code capacities for the design code that I'm using. In this case here, I'm using the Canadian 086 code. 08619, I believe, if I remember correctly. And you can see here my utilizations as we've shown before. So just kind of retracing my steps there. And then once we have this information and we've defined our design groups, I can go to the run menu and I can go to this design field. And you can see there's a couple different options for design, as you see. I can click on this run design option. And it's giving me a table that shows me all the different design groups that I have. And then I can specify my design method. So is it going to base it on different criteria that are selected in the field next to it, or based off of the order of my section list? So you can see here the criteria that we have. Is it going to choose the one section that has the lowest cross-sectional area, or maybe the lowest depth, or some other criteria that we might have? And we can also choose whether we want to run all the designs for all the different design groups or not, and even fine-tune our design groups here if we need to. So I'm going to click the Run button. It's going to go through another analysis and basically find new cross-sections for my members. Now, it's worth noting here that the analysis results, which are the demands on my structure, these are all based off of my original cross-section sizes. So those cross-section sizes are perhaps smaller than what we'll end up with here. And the loads that come from them won't necessarily represent the loads that would be on our updated structure, but we can iterate through this process fairly simply. So I can go to the Run menu here. I can go back to Design, and I can see Timber Member Design, Use Design Sections. And I can see the results that it's come up with here. So it's showing me for each of my design groups, the original cross-section, and then the design section and the utilizations associated with each. So if I wanted to, I could use this design section and say, okay, we're going to update the model with this design section. Or maybe I can override the section choice that is selected and use something else instead. So I'll click Apply here, and it's going to swap out those sections. And I don't know if it's obvious, but you can see here there is a slight change in the cross-section size. Now for our columns, for example, we're using a glulam 80 by 228 section. And it might be worth me code checking this again. And the reason is kind of related to what I said earlier. All of the demands are based off of our original cross-section size structural analysis. So if we want to reanalyze with this new cross-sections that have a different mass, they have different stiffnesses, maybe the force distribution, where the forces are going is changed too, based off of the relative section size change, we can do that here. So I can go to run, code check again. And it's possible if we have a large change in our cross-sectional size that those demands that drove the design of our sections originally might not necessarily have been an accurate kind of representation of the forces that would exist in a real model once we resize those sections. So we might get some failing utilization still, and we can certainly address those. So we're just running the code check now with the updated cross-sections. And again, when we're looking at things like self-weight and so on, we will get new masses. So you can see some of my masses or some of my columns are still failing for bending plus axial. So I would need to look at this as well. So let's just go ahead and repeat this design process. I'm going to say run design. But this time, I'm not so concerned about my beams. I don't really see any issues with what's going on there. So I'm just going to work on the columns here, and I'm going to run just the column design. And we'll see what it comes up with here. So running just the column design, we're going to leave all of those beam section sizes the way that they were originally from that design. And now if I go to run design, timber design, use design sections here, I can see that originally it was using an 80 by 228 section. Now it's proposing a glulam 175 by 190 because there's more load on it from the larger section sizes. I can decide, do I want to stick with this one, or excuse me, or maybe do I want to override the design? So here it's still a pretty big jump in the section size. So I could say, well, let's just go up a little bit. I'm going to go with a 215 by 266 section. And it'll just give me a little bit more comfort. That's just an idea that I propose. And now we can see the cross-section size has indeed changed. And I can go to the run menu one more time and code check this guy just to make sure that everything is, excuse me, all hunky-dory for the new cross-section size for all of the structure, not just our columns. And we'll be able to see those results quite shortly. So it's running the analysis again with new cross-section sizes. And we'll also see shortly the utilization ratios that we get out of this. And we can look at the results in a tabular format or even print a PDF report. So here I can see my utilization ratios. This is showing me the governing code check is now timber member two-way bending rather than what was before. I believe it was axial. Was it axial forces? It must have been for my columns. So you can see the utilization ratios are still quite high, but they're below 1. We can further fine tune this if we want to. And if I go to the timber code checks, I can see here all the utilizations are less than 1 when previously we were having results in the, I think it was like in the 5 utilization. So 5 times our demands or capacities. And if I look at the quantities, not surprisingly, I can see a different looking table, first of all, and significantly changed mass results, which would make sense. Now I've got more cross-section sizes. The lengths have remained the same, but naturally the mass will add up to be quite a bit higher than what we had before. So that's, what we would expect if we were having undersized sections, but it's something that allows us to perhaps drill down into the design and make sure not only are we passing the code checks, but we also have a more efficient design. And in this scenario, we can see that some of the utilizations in our interior columns, for example, are fairly low compared to the external columns for this particular code check and this result here, or this load combination. So that might be an indication that perhaps we could subdivide our design groups more if it made sense from a constructability perspective. So that's totally subjective to your own preferences, but it's something that you could certainly consider. And if you'd want to review any of these results here, you can click on them, and I can see for any one particular load combination, I can look at a specific member in detail and see the resistances, the clause references, and so on. This is for my two-way bending check. I can do the same thing for, let's say, bending plus axial, and I can see what went into this particular check for both the demand and the capacity, all the different inputs that are considered. So we can verify that the assumptions made by the software and the factors used are consistent with your expectations.